Over the course of this explainer series, we've looked at the mind-bending reality of building these towering artificial minds, right? I mean, we've mapped out hundreds of millions, sometimes even billions of parameters. We've talked about these sprawling, massive server farms. We're talking millions of dollars in electricity alone, and these liquid-cooled supercomputers that have to run at absolute maximum capacity for months on end. And what's it all for? It's all just to teach a machine how to speak and understand human language. The physical and financial scale of this, it's literally almost unfathomable. But today we're gonna flip the script entirely. Because today, we are gonna look at how a teenager sitting in their bedroom can take one of these massive multi-million-dollar models, fundamentally change its entire personality, and teach it brand new, highly specific skills. And the crazy part? They can do it using nothing but a standard off-the-shelf gaming laptop.
So, how is that even possible? To understand how the most expensive technology in human history was essentially hijacked and democratized by the open source community, which is this amazing global network of independent researchers and hobbyists, well, we have to look at what I like to call the Great Compression. It's basically a brilliant mathematical cheat code. It took the massive, sprawling, incredibly heavy architecture of artificial intelligence and shrank the workload down so much that anyone, practically anywhere, can actually use and modify it. Welcome to the overview effect, where you zoom out and everything changes. Section 1, the hardware barrier. Okay, so in our previous discussions, we explored how you go about fine-tuning a foundational model. Taking this wild, feral, text-predicting algorithm and carefully training it to become a polite, helpful assistant. But there is a dark, incredibly expensive reality to this standard fine-tuning process. When you traditionally fine-tune a model, you use a process called backpropagation to update the model's weights. You essentially have to touch, evaluate, adjust, and then rewrite almost every single one of the model's internal knobs based on its errors. If you're using even a basic, older model, let's say something like GPT-2, you are updating 124 million individual parameters. That requires a massive, massive amount of computer memory. Why? Because you aren't just storing the model itself. You are storing all the complex gradients, the error rates, and the optimizer states for every single one of those 124 million numbers simultaneously. To really put that into perspective, every single time the model makes a guess, the computer has to map the error backwards through all 124 million connections, calculating a tiny, microscopic adjustment for each and every one. And it has to do this thousands, if not millions of times.
Which brings us to a harsh reality. For most of us, if we tried to rely on a standard consumer graphics card to do this, it would result in an instant crash. Your hardware would be completely crushed under the sheer weight of all that data. There's just no way around it. Because of this, the industry standard relies on those massive liquid-cooled supercomputers, the kind that only trillion-dollar tech giants can actually afford. For a brief moment in the history of AI, it honestly seemed like artificial intelligence would be permanently locked away behind this massive hardware barrier. It felt like only giant corporations would ever have the resources required to modify and actually control these minds. But the open source community, they absolutely refused to be locked out. They started hunting for a backdoor, a way to sidestep these ridiculous compute requirements. And in doing so, they asked a really profound question.
They asked, what if we don't actually need to change the brain to teach it a new trick? Section 2, freezing the foundation. To see how this idea actually builds into a real workable solution, we have to look at an amazing bypass technique known as LoRA. That stands for Low-Rank Adaptation. LoRA is the exact method that prevents your computer from having to recalculate every single number. Now, to understand it, let's anchor the abstract math visually for a second. Deep learning relies heavily on tensors. Now, don't let the word scare you. That is just a fancy mathematical term that generalizes how we group numbers together. It ranges from single numbers called scalars to lists called vectors, all the way up to 2D matrices. Think of a 2D matrix just like a massive spreadsheet grid of numbers. Inside a large language model, a single layer's weights might be represented by a grid that is 10,000 rows by 10,000 columns. If you multiply 10,000 by 10,000, you get 100 million. That means there are 100 million individual numbers packed inside that single grid. During traditional fine-tuning, your computer is actively calculating and storing updates for every single one of those numbers. And if you have dozens of layers, you are very quickly dealing with billions of calculations for every single step of training. It is a total logistical nightmare. But LoRA completely bypasses this entire problem. The very first step of this incredible cheat code is placing a digital lock completely over that massive original matrix. This process is called freezing. The engineers literally freeze the foundational knowledge of the machine in place. Think of it like it's locked in amber. The pre-trained weights, all those billions of parameters that took months and millions of dollars to calculate in the first place, they are secured behind an impenetrable wall. They cannot be altered and they cannot be touched. And because it's completely frozen, your computer doesn't need to waste a single byte of memory calculating how to change it. All of those optimizer states, the gradients, the constant error tracking, all of that heavy computational baggage is just dropped. Completely. Gone. Next, they build a bypass. They create two brand new, incredibly tiny matrices, and they place them right next to the massive frozen one. Think of it like a river that suddenly hits a fork in the road. When new data flows up through the neural network, it hits this fork. The mainstream of data passes completely unaltered straight through the original frozen brain, carrying all of that incredibly deep foundational knowledge. But simultaneously, a small side stream of data passes through our two new tiny matrices. Finally, at the end of the path, the results from both streams are mathematically added back together. Now here is the absolutely brilliant part. The computer only has to train that tiny side stream. The massive frozen brain does all the heavy lifting of general comprehension, like understanding English grammar and logic, while the tiny side stream acts as a specialized little filter that just tweaks the final output. But you're probably asking, how does training two tiny little matrices actually change the behavior of the entire massive model? Well, it's all based on a mathematical trick called matrix decomposition. Essentially, we trick the computer into doing massive math using just a tiny fraction of the numbers.
Section 3, a 99% reduction.
Let's actually do the math on how this 99% reduction works, because it's fascinating. We need to see exactly how these tiny adapter matrices can possibly mimic a giant multi-million parameter matrix. See, we need our two tiny matrices to output a mathematical shape that perfectly matches the massive 10,000 by 10,000 grid. Why? So they can be smoothly added together at the very end of the process. But instead of building another massive grid to match it, LoRA does something incredibly clever. It builds one tall, incredibly skinny matrix. Let's say this one has 10,000 rows, but only 4 columns. Then it pairs it with a short, incredibly wide matrix. The second one has only 4 rows, but 10,000 columns. It honestly sounds incredibly simple, almost too simple to actually work, right? But this specific geometric arrangement is the absolute secret to the whole bypass. Let's look at the actual numbers here. That tall matrix has 10,000 times 4, which gives us 40,000 numbers. The wide matrix also has 4 times 10,000, which is another 40,000 numbers. If we add those up, together, these two tiny side matrices contain exactly 80,000 parameters. Okay, so the absolutely crucial point is this. We have successfully mimicked the physical output shape of a 100 million parameter grid, but our computer only has to track and train 80,000 knobs. We have literally reduced the memory compute requirement by over 99.9%. That tiny fraction representing what we actually train is practically invisible next to the massive frozen foundation. This means you absolutely do not need a liquid-cooled server farm anymore. A standard consumer graphics card, the kind you'd find in a good gaming laptop, can easily handle the mass of updating 80,000 parameters. You have essentially collapsed a massive mountain of data down into a tiny molehill without losing the ability to steer and guide the mountain itself. It's genius.
Section 4, merging the knowledge.
Now, you might be wondering, what happens after you train these tiny matrices? Like, do they just sit there forever? Well, when the training is finished, you don't even have to load them separately every time you want to use the AI. Because of the rules of linear algebra, you can just mathematically multiply the two tiny matrices together and permanently add those resulting numbers directly back into the original frozen weights. You essentially bake the cheat sheet directly into the brain. It's like, instead of trying to rewrite an entire massive printed textbook just to add a new idea, you simply write some brilliant notes right there in the margins. You see, we spend our entire journey in this series building an impossibly massive, expensive, and fragile structure. We literally mapped human thought into hyperspace. But because of this mathematical cheat code, because of LoRA, the power of that massive structure no longer belongs exclusively to the people who built it. It belongs to anyone who knows how to write in the margins. The giant was built by the few, but it is steered by the many. When you look past the sheer, overwhelming scale of artificial intelligence, you start to realize something truly profound. True innovation isn't always about brute force. It's not always about just building something bigger and faster and more expensive. So I want to leave you with this thought. What if the future of technology isn't about massive scale at all, but simply about finding the most elegant shortcut? Thank you so much for joining me on this explainer. If this journey changed how you see the world, keep that curiosity alive. Keep looking for those elegant shortcuts, and I'll catch you in the next